You have to have a complete understanding of what's going on in the multivariable function. So I'm going to compare the difference between the single variable case and multivariable case. So in the single variable case, your function, it has one independent and one dependent, and the derivative at certain point is also limit, but it's just the ratio of two numbers. And we have the theorem that f is continuous at a implies, so this is one statement, that, differentiable. Implies that f is continuous at a. Okay, so that's a single variable case. And let's look at what's difference between what's different in the multivariable case. Of course, our function, I'm going to write down the most general form of multivariable function. So usually sometimes we put the same symbol f for multivariable as a single variable. But if you look at this pair of points carefully, it's just a pair of numbers, right? So when you have a pair of number, you can always think that as a vector. So sometimes you put a vector notation here, and we call these points to be also kind of position vector, pointing to that point in the n-dimensional or n-dimensional space. So anyway, that's a multivariable function. And in this case, our derivative, so here, A is now a point in n-dimensional space, so I put a arrow sign here so that you don't confuse with A with the number A there. So it's n-dimensional point here. And sometimes you can still write the f prime A arrow in order to represent the derivative, but sometimes I'm going to write df in order to distinguish that it's not a number. So this is the n by m matrix, m by n matrix. So there are m columns and m rows and n columns. So here, there 1, there x, a. So everything is in the matrix is a partial differential, not partial derivative. So it's a number. So f, y, x, n, a, and here y, m, x1, a, y, m, x, n, a. Okay, so that's the definition. And you have to be careful that even though you could have a partial derivative, it doesn't mean that the function f is always differentiability. So here is a theorem. So let me state a proposition first, and three proposition, and I'm going to give you the relation between these three. So f is continuous at point A. So this f is a multivariable function. So this is one statement. It's not a theorem. It's not a mathematical statement that you can prove to be true or false. It's just claim. Okay, so this is the condition or just the claim, and f the directional derivative of the function exists for all vector u. So that's a second claim. So I'm not saying the function is satisfying this. I'm just a simple claim. Okay. So and then f is differentiable at x equals to a. And the last one is that the partial derivative f of x and f of y are continuous at x equals to a. So there are four claims, and the implication between these four claims is the following. So 4 implies 3. 3 implies 1 and 2. Okay? That's the only statement you can make. So therefore, let's say 4 implies 3. So the statement could be if the partial derivative, two partial derivative of the functions are continuous at the point A, then the original function is differentiable. That's true. Okay? but converse is not true. So even if you have a function which is differentiable at the point A, it doesn't mean that the partial derivatives are continuous. Okay? So differentiability implies that partial derivative exists, but doesn't mean that it's continuous as a function. And same for 3 implies 1 and 3 implies 2. And also 1, 2, there's no relation. So look at this one. Oh, what's the question? Well, you talked about differentiability and the directional derivative. So look at this, 3 implies 2. So if function is differentiable, then the second claim says the directional derivative of the function at the point A exists for every direction. That's true. That is true. But the converse is not true, which means that even if you have a directional derivative of the function at the point for every vector u, it doesn't mean that function is differentiable. It does not mean the function is differentiable. I'll give you an example. So here is the graph of the function. Here is y equals to x squared. So as a function, let's define a function xy equals to either 0 or 1. So this is a line hovering above xy plane at the level 1. And this is 1 if y equals to x squared, but xy is not 0, 0, and 0 otherwise. Okay? You see what it means? So there is a missing point on xy plane. Almost everything is 0 except for the point on the y equals x squared line on xy plane. But at the origin, it's not above the xy plane. It's actually on the xy plane, right? So let's look at the directional derivative of this function at 0, 0. So what's the definition? T goes to 0, and let's say u is a comma b. So we have at bt minus 0, 0, right? So I omit 0 plus at, 0 plus bt because it's obvious here. So I just want to move away from the origin in the direction of u by a certain amount and see the value of function, and then take the difference, and then take the ratio, and take the limit. So what is the value of f at, bt? So look at this picture. You have, where is at, bt lies on? So if this is your vector u, it lies on the line, on the straight line, on xy plane, right? So according to t, what t we speak, then you have away from the origin. If t is 0, then you get the origin, right? So at some point, maybe there could be intersection between y equals to x squared and this line. So at that point, maybe the function value is 1. But we're not looking at this specific point when you take the limit. I take t goes to 0. So, and also t is small, then there's no chance there is an intersection between line and the parabola here, right? So this is always 0. And how about what is f0, 0? So we assume to be 0, right? And what? Over t. So it's 0 anyway. So the directional derivative is 0, right? Okay, so 2 is correct. 2, what did it say? Directional derivative exists for all u. Okay, so did I mention specific u? No, it can be anything, right? So whatever that is, I have 0 directional derivative, which means that what is partial derivative at 0, 0? 0. Everything is 0. Okay. Now, let's check whether 3 is true. So we have the second condition. Let's see if 3 is true in this case. So f being differentiable means that if we take the linear approximation of the function at that point 0, 0, then the limit between, xy goes to 0, square root x squared y squared fxy minus lxy goes to 0, right? So this is the differentiability. So what is the lxy? So lxy is 0, 0 plus fx 0, 0 x minus 0 fy 0, 0 y minus 0. I know that these two are 0. I know this is 0. Everything is 0. And if I want to show this, then what I have to show is f of x y over x squared plus y squared when xy goes to 0, 0 is 0. I need this in order to claim that 3 is true. But it is true. So fxy is either 0 or 1. It's almost 0, but we have to exclude the exceptional case that xy lies on this parabola, right? So the limit says no matter how xy or what kind of route that xy takes to approach to 0, 0, this limit has to be always 0. So what if I take this path? What if I take xy on the parabola and then approach to 0, 0? If I take this path, then what is my value of function? It's always 1, right? So if xy follows y equals to x squared, then so I can just take x or y, one of them, because the other is determined automatically. Let's say x goes to 0. And then the value of function is always 1. 1 over square root plus y squared. So what is the limit in that case? So y is x squared, so we get x fourth, right? So when x goes to 0, what's the limit? Infinity. The limit does not exist. So therefore, it's not 0. So therefore, it's not differentiable. So this is the example where you have all the directional derivative for every direction at that point, but still not differentiable. So the main difference is differentiability is not about partial derivative. Partial derivative is somehow kind of a tool or kind of computational tool to deal with the differentials like this one. The meaning of differentiability is that you have a tangent plane of your graph of the function so that this tangent plane, tangent flat plane, it somehow approximate the value of function so well so that the error actually decreases much faster than the speed of point approaching to that point. So here we are looking at the tangent plane at the origin, which is the actual origin in the three-dimensional space. And we kind of expect that the tangent plane to this graph, so actually the graph is a flat plane except for this dot line here because it's over this line. It's just xy plane. The tangent plane is xy plane itself. But there is an error. Here, the big error, these big errors, right? These big errors. This error is not decreasing at all as xy approaches to 0. It's still always 1 until the very moment that it touches the 0, 0. So the error is not approaching to 0. Therefore, it cannot be differentiable. So in that sense, it's obvious, right? Without going into the definition, you can still define or prove why it's not differentiable, but you have to get the correct intuition what is meant by differentiability. Differentiability is about error estimation, okay? And also, this example tells you that this 1 and 2 is not related. 2 is satisfied for this function. Is this function continuous at the origin? Is this first one satisfied for this case? Is it continuous at the origin? No. Why? So continuity is about approaching to that point, whether your value of function is approaching to the same value. So if you approach to 0 in a straight line, you always get to 0 because you're following the line on xy plane. But if you follow the paraboloid line, like parabola here, then the graph on that parabola line is above this xy plane at the level 1. So if you follow this line, the value of function approaches to 1. So you're not always getting to the same point. It could be 0 or 1, depending on which path you take. So 2 does not always imply 1. So that's the main difference between the single and multivariable. Multivariable kind of saying that if it's differentiable, then it's always continuous. But what is it saying here? So differentiability, the third one implies 1. That's true. But the second one about the differentiability of partial differential does not imply the continuity. So the partial differential is not really generalizing the differentiability of a single variable function. It's somehow the concept of partial differentials and the normal differential of multivariable function collapse into the same concept in a single variable, but that's only because single variable have only one variable, because it's too simple. You don't have no way to distinguish these two. But in the multivariable, these two concepts are different. Partial differentiability or partial differential is not differential. Okay? Okay. Any questions? Okay, so let's continue our discussion about optimization. And let me give let me start from the definition of critical point. All right, so optimization. Again, whenever you see any words, you have to have clear idea of what that means. The optimization is finding minimum or maximum. Of what? Of course, a function, right? So you have to have some kind of function that you can calculate its value, and optimization is finding when does that function attains minimum or maximum values. So here is the definition. So there are many ways you can visualize the function. So if you take the graph of the function drawn on your computer and then kind of see where the highest point is and lowest point is, that's a good way of doing it. But sometimes you actually want the exact coordinate of the minimum point and maximum point. So you have to go for the critical point. A critical point of a function. Let's say our function is two-variable function. Is either first a point that is not continuous, or a point that is not differentiable, so I forgot to mention that the point that function is not continuous. Okay, I forgot the noun here. So the function f is not differentiable at the point. And the third one is a point where both, so let's say point A, where f of A, or x0, y0 in this case, because we only have two variables, x0, y0, where f of x and f of y are both 0. Y are both 0. Okay, so we call a point critical point if any of these three satisfied. So you cannot have more than one thing satisfied at the same time. So it's either not continuous, or if it's continuous, then it's maybe not differentiable, or it's continuous and differentiable, but the partial derivatives are all 0. So if that's happening, one of these happening, then its critical point. So what is the case of not continuous here? So not continuous, let's say we have a graph like this, but let's say we have a hole, kind of a missing point on one point, and the actual value of the point at that point is way higher than every point else. So then this is kind of maximum, right? Or it could be lower than every other point, then it could be minimum. So anyway, so if it's something going on, something not continuous, discontinuity going on, then you have to check manually whether this point has a higher value or lower value than the neighbors. So that's the first case. And how about when it's not differentiable? So you could have this kind of a cone, So you have a tip, which is sharp corner. So this is also maximum, right? Or if it's inverted, then it's minimum. So something going on, so you should check what's the value and how the value of neighbor points are distributed near that point to see whether that's maximum or minimum. So I'm saying that it could be neither. So it could be neither max or neither min. It means it's saddle. But anyway, you have to check. And the third one is most case, something that's nicely going on here. So let's say we have a nice paraboloid upside down, and we have a tip, the highest point to be the maximum. Then you can see that this is maximum by drawing the graph, but there is another theorem that you can check by looking at the values of certain function, whether it's maximum or minimum or saddle point, which is a Hessian. So anyway, so these three cases are all the cases of critical point. And let me define one more thing here. A critical point is called local max, local min, or saddle if, so let's say the critical point to be x0, y0. So and also this is local max of a function. So if f of xy is always less than equal to for all xy near x0, y0. So near means that sufficiently near. So it could be diverging to infinity after long distance from the main point here. But if I take sufficiently small neighborhood around that point, then every point in that neighborhood, except for the point, base point, value of function is smaller than equal to that value of function at that base point. That's the local maximum. And the same thing, if the opposite inequality holds, then it's local minimum. And if neither of those happens, it's called saddle. So there are three categories of critical point, either local maximum or local minimum or saddle. And the spirit is basically when you take the optimization, you want to go for the global maximum and minimum, global. So what is the difference between local and global? Local means that you only check the neighborhood, small neighborhood. Global means that you check entire domain. So optimization usually go for the minimum value among an entire domain. But you have to start from local maximum, because if it's global maximum or global minimum, it is local maximum or local minimum. So you could have a global max or min among the candidates of local max and local min. So find all the local max and local min and then see the values. Maybe there are finally many local max and local min, or find a category of the values and you can choose the minimum and maximum to get the global max or global min. So that's the point. So let me give you another statement just as a review about the Hessian. So let me erase this. So if x0, y0 is of the critical point of the type 3, so this type, that it's differentiable, then there are three categories. So here, first, look at the value of second order derivative, and then you look at the value of the function d, where d let's see. Let me write it here. So D is fxx fyy minus fy squared. And if it's positive, then depending on the value or sign of fxx at that point, you can have a local max or min. And if it's negative, then it's saddle. So in this case, to have a proper saddle point, your fxx shouldn't be 0 here. So anyway, so let's look at the example. Any questions before we move on to the example? So here we have f of xy equals to xy 1 minus x minus y. Let's look at this one. Okay, so I want to see all the local maximum, local minimum, and also find the global minimum and global maximum on the entire plane. So this happens for every point in R2. So first, there's no discontinuous point and not differentiable point because this is polynomial. Polynomial is always continuous and differentiable. So we have to go for the type 3 critical point. So let's find f of x and f of y and see at what point these partial differentials are 0. So what is f of x? Y, 1 minus x minus y plus x minus xy minus xy. And here, symmetric. 1 minus x minus y minus xy, right? So this one is y minus 2xy minus y squared. So actually, you can just pick a factor of y. So we have y 1 minus 2x minus y. And this one is x times 1 minus x minus 2y. So I want to find out the value of x and y that these two equations are satisfied. So there are 4 cases, right? So if you want to make the product of two numbers to be 0, either one of them has to be 0. So it's either x is 0 and y equals to 0, or 1 minus 2 minus y equals to 0, but x is 0, or y is 0, but 1 minus x minus 2y equals to 0, or 1 minus 2x minus y equals to 0, and 1 minus x minus 2y equals to 0. So in this case, it's 0, 0, of course. And in this case, it's 1, 0. In this case, it's 0, 1. And in this case, 1/3 and 1/3, right? So 0, 0, 1, 0, 0, 1, and 1/3 and 1/3. Okay, so there are 4 candidates of critical points. I don't know which one is local max, min, or saddle. So let's use this theorem. This is Hess's method. And, so let me erase this part. So first, let's compute fxx. Okay. What is fxx? So this was fx, right? I want to take a second derivative. So when I do that, y is okay, minus 2. So it's minus 2y, right? That's fxx. And what is d here? So d is fxx, fyy minus fxy squared. So I know what fxx is. It's minus 2y. And the original function is symmetric function. You can change x and y to get the same thing. So fyy must be just symmetric to fxx, which is minus 2x. And fxy, so this is fx. Let's take a derivative of y again. So this is minus 1 minus 2x minus y. So I'm taking derivative of y. So that's the first factor, and then I get minus y, right? Square. Okay, so what is it? So let's see. It's a 4xy, right? And then this is minus 2y squared. So it's minus 1 minus 4x squared minus 4y squared. Plus, sorry, so plus. Minus, because we have a minus sign. So minus. And then plus 4x plus 4y. And multiplying these two, I get canceling with this, right? So I get canceling of these. Okay, so that's my D. That's my formula of D. So now let's see the value of fxx and D at these 4 points to use this table. So this is fxx and this is D. What is fxx at 0? It's 0, right? And what is the D? Minus 1, yes. And then what is fxx at 1, 0? Still 0. And what is D at 1, 0? Y is 0. X is 1. So it's still minus 1, right? And how about 0, 1? So x is 0, y is 1. So cancel out. So still minus 1. And this is minus 2, okay? And then what is f of x at 1 over 3? It's minus 2 over 3. And what is D? I think I should compute. So minus 1 plus minus 4 over 9 plus 4 over 3 minus 4 over 9 plus 4 over 3. Okay, so this one is 9 minus 9 minus 4 plus 12 plus 12 minus 4. So this one is minus 17 plus 24. So 8 over 9? No, not 7 over 9, sorry. 7 over 9. Okay? So we don't go for the value, we go for signs. So here, I think I really don't need this one. So as long as the D is negative, what is the classification of that critical point? So these are saddle point. Okay? Doesn't matter what value of the fxx is, because D is always negative. So here, the last one, D is positive. So now we can determine whether it's maximum or minimum according to the sign of fxx. So sign of fxx is negative. So therefore, what is it? Maximum or minimum? What does it say? Yeah, maximum. Let's try to graph this and see what it looked like. So it's just a simple drawing of a graph of function. So numpy and xy. So I want to set my xy to be range in between some number that covers all these 4 points. So maybe I can, let's see, lin space from 0, not 0, minus 1 to 2, I guess. That covers that point. Minus 1 to 2. And then z is fx y 1 minus xy, right? Okay, so x is what is the forgetting about this three-dimensional picture. So let's see. Let's see, what was the, how do we draw a three-dimensional picture? See. PLT figure. Okay. Okay. Projection at subplot. Yes. Okay. Let's not color it. Let's put edge color to be K. Oh, that's too much. Okay, let's not put it here. All right, so if you look at the graph of the function, so this is how it looked like. So I'm going to put the dots for those 4 points and see what happens. So axis, so 4 points, x, y to be pi array of what? 0, 0, 1, 0, 0, 1, and 1 over 3, 1 over 3. So let's plot x, y dot transpose and color red. Oh, okay, so dot. Just RO here. Okay, so it's actually covered with a surface, but you can see vaguely where that is. Maybe I can put an alpha here to make it bigger. Yeah, so you can see that this is 1 over 3, 1 over 3, and 3 points. Maybe this is 0, 0, right? So by looking at the graph, the big picture, you don't really see what's going on. It looks like everything is just minimum point for me. So what you have to do to figure, really check whether that's really the case, you have to enlarge the picture around that point. So let's do that here. So I'm going to use the same plotting here, but using different range here. So x0 and y0, let's check at 0, 0. And I'm going to put the epsilon to be 0.1. I think 0.1 might be okay. x0 minus epsilon, x0 plus epsilon, and then y0 minus epsilon, y0 plus epsilon, and do the same thing here. And okay, so we have surface drawing and plot x0, y0, red color. Now you can see that this is actually settled. So I draw 0, 0 and the graph of that function near that point, and you can see that this is concave down here and concave up, right? So if you move along this line, the value of function decreases, so therefore it kind of local maximum along this line. But we don't call it local maximum because whenever you say local critical point, then you have to satisfy this inequality for every point near that point. So if you're moving along this line, the points are actually higher than this point. So you cannot tell whether this is local maximum min. So therefore it's saddle point. And same happens for other 2 points, but let's check what happens 1 over 3. So here, just changing x0 and y0. Okay, so I have to plot this x0 times y0 times 1 minus x0 minus y0. Okay. Plot, what is it? Plus 3D? Okay. Why is it? X0? X0. Oh, I forgot this one. Okay. 1, 2, 3. Just plot. Yes. Okay. So here now we have part of a graph around 1 over 3, 1 over 3, and you can see that it's the maximum point, local maximum. So you cannot see that in a big picture because, so it's very subtle. The height change is very subtle. You can see the scale is very small compared to the scale on XY. So in the big picture, like I draw here, it doesn't really tell that this is local maximum, but we checked by graphing the function near that point, and also you can check by Hessian's, Hess's method. And if you're like thinking about the height of a mountain as a two-variable function, so let's say height h here, and then you can draw the contour lines of this height function like this, right? So you have the highest point of your mountain right here, and then this contour line is where you have the same height along the way. And at every point, let's say you're at here, longitude and latitude, you want to go for the perpendicular direction of your contour line to get down to the mountain, the ground, the fastest way. So that's because this is the gradient vector, gradient direction, and gradient direction or opposite. So it's a gradient direction here, and you want to go for the opposite direction of the gradient, because that's the direction where you get the fastest change of your function. Okay. So remember these two theorems. So we proved this theorem, and this theorem is actually comes from the chain rule. So you may, if you have a question, I can prove this to you next time. So maybe tomorrow, not tomorrow, next week, we're gonna talk about the project 6, which is about making a neural network.